Hey guys, how's it going? So today we're gonna be going through NextVIT, next generation vision transformer for efficient deployment in realistic industrial scenarios. So firstly, we're gonna go through the paper and understand the theory part of things. Then we're gonna go through the code and try to code it up. So yeah, I've been quite a fan of like these hybrid architecture whereby we try to integrate CNN and Vision Transformer. They both have their own pros and cons. Like for instance, CNN can be quite good at capturing local information. With Vision Transformer, they can be quite good at capturing global information. However, given the time complexity of Vision Transformers, they can quite increase latency if they are not designed correctly. So I pretty much appreciate the authors here. They try to design these two components in such a way that they increase accuracy at the same time they increase decrease latency, I mean to say. So yeah, I was quite impressed with the approach. So without wasting any time, let's get into it and understand what they did. Given the limitations of VIT and CNN and their prongs, the author did ask themselves if would it be possible to build a vision model that can be able to infer as fast as CNN but also perform as powerful as VIT. Based on this, what they did was to design the next convolutional block and the next transformer block, which we're gonna get into. The main reason of this was to capture the local and global information with the deployment friendly mechanism in mind. However, to stack these two components, also they realized that can actually increase latency, so there has to be a way we stack them in a correct way. So what they did was to introduce this next hybrid strategy, which is designed to stack these two components, the next convolution and the next transformer block, in an efficient hybrid paradigm way. So before actually designing these two components, the author did analyze the transformer model, and they realized that one of the key factors that was increasing their inference time was the quadratic complexity with respect to the token length of the attention mechanism, right? Another component was the non-floatable layer norm and GALU layers. Okay, so the authors did actually try to analyze previous architectures like mobile VAT, and one thing that they realized is that these previous hybrid architectures, they adopt convolutional block in a shallow stage and just stack transformer block in the last few stages. However, based on their observation, they realized that these hybrid strategies is effortless to lead to performance saturation on downstream tasks such as segmentation and detection. So to address these bottleneck and these findings on the previous papers, what they propose like three important components to design efficient vision transformer. So they firstly talk about the next convolutional block, which is skilled at capturing short-term dependency information in visual data with novel deployment-friendly multi-head convolutional attention. So, and secondly, they build the next transformer block, NTB, which is not only an expert at capturing long-term dependency information, but also work as a lightweight and high low frequency signal mixer to enhance modeling capability. So essentially, a signal mixer is a process of combining two or more signals to create new signals. So you can think of combining different token sequence. This could be based on their importancy, and right. So what they mean here by CNN is skilled at capturing short-term dependencies, that CNN operate on a small window of the input, right? You can think of that kernel. So this makes them better at capturing short-term dependency. So we can say local patterns. They can see only limited amount of text. Actually, sorry, let me just zoom in here so that you can see. So they can see only a limited amount of text. or image or something like that at the time, right? Whereas with a transformer, the transformer model, they operate more of on a sequence, so they can capture long-term dependencies. So this is due to the model weighting the importance of different parts in the sequence. So this is also known as global pattern, right? So here the author continued that finally we design a hybrid strategy to stack this next convolutional block and the next transformer block in a novel hybrid paradigm in each stage, which greatly reduce the portion of the transformer block and retaining the high precision of the vision transformer in various downstream tasks. So before we get into this, I thought it would be a good idea for me to show you the high level architecture of the model design. So the first component is the next convolutional block. So it's composed of the group convolution of 3 by 3, and we have a batch number value and pointwise. The next block, the next transformer block, is also composed of these components. So the first one that we're going to talk about is the next convolutional block. So I'll keep on coming to this architecture and show you where we're currently at. And yeah, so for now, don't worry about what's inside here. So we're going to discuss each and everything and come back to this. So for now, we're going to talk about this component. This is our first component that we're going to talk about. So scroll down. So it's going to be the next convolutional block. So what the author did was to revisit some of the classical structural design, one of them being the bottleneck block proposed by ResNet. So what is this bottleneck block? So you can think of it as like we have some sort of like an input feature map, right? And then we pass this towards a 1 by 1 convolutional layer, conv layer. So the purpose here is to reduce the feature map. So it's going to be reduce feature map. Then we pass this towards a 3 by 3 convolutional layer. So the purpose of this is to actually be able to extract features, right, from the reduced feature map. So we extract features here. Okay. Then the next step is to apply a 1 by 1 conv layer again. So this one is actually going to increase the feature map, right? So we increase so that we allow the dimension of this and the input feature to be the same, because the last step essentially is going to be to try to match these two. Oops, where is this? Okay, so we try to match the input with the output from the 1 by 1 convolutional layer. But essentially this is what the bottleneck, what they're referring to in this case. Anyway, they realized that, okay, with this bottleneck, although it had its dominance in visual network for a long time, but because of its inherent inductive bias and deployment-friendly characteristics, however, the effectiveness of this bottleneck is inadequate compared to the transformer block. Even the Convent XT block tried to modernize the bottleneck by imitating the design of the transformer block. So what they're saying is that the transformer model is still quite superior. So the transformer model has achieved excellent results in various visual tasks, and its intrinsic superiority is jointly endorsed by the paradigm of metaformer. So yeah, what do they mean by this metaformer? So let's try to understand this. So metaformer essentially is an architecture that is composed of, firstly, the input embedding. Just gonna write here embedding. So we can think of this embedding, essentially it has to project the input tokens into the embedding space, right? Then these tokens pass through a series of metaformer blocks. So we have two blocks here that you can think of, right? Then what we do is that these two blocks, they consist of residual connections, like so. Okay. Usually there's also a norm. Here we normalize the input tokens. Then the first block is this token mixer. It's called token mixer with a normalization and a multi-layer perceptron. So the token mixer purpose essentially is to communicate information across all the tokens, right? So it allows information to pass between channels. Okay. Then here we have, I think we have multi-layer perceptron. So we have a varied different types of metaformer architecture. So what happened is that this token mixer, it could be an attention mechanism, right? It could be a spatial multi-layer perceptron. It could be a pooling, right? Then we pass this towards a norm. Then we have channel multi-layer perceptron, like so. So just to paste this image here so that you can see what I'm talking about. So these have been like various architectures introduced by different papers. But yeah, this is like the metaformer general architecture. So you can see that we have an input embedding, norm, token mixer, norm, and channel multi-layer perceptron. The point that I'm raising here is that in this paper that we're currently looking at, the next convolutional block essentially followed the metaformer. So, and this architecture is like so. But now the question might be, then what did they include in this token mixer? So for them, let's go to the architecture. They included a group. A group convolutional of 3x3. Then they took that towards a convolutional of 1x1. Then they had again residuals. Then they passed that towards a multi-layer perceptron. Obviously, I'm assuming that's a channel also. Multi-layer perceptron. Then they had another residual connection. Then they had the output. But we can see how different their implementation is from the previous one. This one had a pooling. So yeah, we're gonna try to understand now why they included that, the intuition behind their implementation. So the authors state that the next convolutional block follows the general architecture of the metaformer, which is verified to be essential to the transformer block. An efficient attention-based token mix is equally important. Therefore, they decided to design a novel multi-head convolutional attention as an efficient token mixer with deployment-friendly convolutional operation. So essentially, what they did was to be able to pay attention to different parts of the input. So they designed this thing called multi-head convolutional attention. So you can think of like it uses multiple heads to look at different parts of the input at the same time. Then the output from these multiple heads, then they combine their outputs, then to kind of like get the overall picture. So the question is then, how did they build this multi-head attention, multi-head convolutional attention? Because of this is a token mixer, and if we go back to the architecture, so they built this using the group convolution. So So, so in a way, it's a way of doing convolution, and you can look at different multiple input feature in at the same time. So you can think of a group convolution. It's like in you're given an input feature, the input feature map is divided into groups. Then the convolution operation is applied separately on those input. For instance, let's say we have an input feature map of 64 channels, and we apply a group convolution of 4 groups on this. Then each group is going to apply 16 channel. It's going to have 16 channel, and the convolution is then applied to each group separately. So, in a nutshell, this next convolutional block is this part here. It's the multi-head convolution, and it's used as an efficient token mixer. So it's not only efficient, but it can also be able to have the advantage of the transformer by looking at different input. Yeah, so it can attend to different representation subspaces of the input feature map. So that's the advantage, and that for me was quite mind blowing to think of it that way. But yeah, so that's it in a nutshell, and that's what they're talking about here. Some of these details, they say that beside we adopted efficient batch norm and radio activation function in the next convolution rather than layer norm and GLU in traditional transformer. So like I said, they realized that actually layer norm and GLU actually can be a bottleneck towards the inference. So some of these small details, I think I'll explain them in the code, and yeah, we'll see how they work from there. But yeah, I think at the high level, I say that's how the multi-header convolution work. So we closely observed the multi-head convolutional attention and the next convolutional block. We saw how they actually extract the local representation. So now we're going to take a look at the next transformer block, which is aimed at extracting the global information, which is what the author referred to as a low frequency signal. Based on the previous research, the author did realize that actually the transformer block can deteriorate high frequency information. By high frequency information, I'm referring to local information, that could have been extracted by the CNN. Because of this, what they did was to think of a way they can combine the low frequency signal along with the high frequency signal, and this is when they came up with this next transformer block, which capture what we call multi-frequency signal. Essentially, what they're saying is that we're able to capture low and we're able to capture high. So it's similar thing as global and local information. Okay. So how they did this was to actually, within this next transformer block, was to actually introduce what we call the efficient multi-head self-attention. So how this works is that essentially we take the Z denote the input feature map. So we take the feature, the input, and we divide it into multi-head, right? So you can think of Z1 here, we divided it, Z2 up to all the way to ZH. So we divide it in a form of a channel dimension, right? And this SA here, which is a self-attention, essentially you can think of it as a self-attention softmax query K transpose, and we divide by the scaling factor, and we have a V. So what we have here within this attention, we have these WQ, WK, key, and query, and values. So we can always think of these as linearly for context encoding. Then this P here essentially denotes the average pooling. Then this S here denotes the stride for downsampling the spatial dimension to reduce the computation cost. Okay, so essentially that's what the multi-head self-attention is composed of. So let me just go down. Okay, so they state that we observe the time consumption of the multi-head self-attention module is also greatly affected by the number of channels. So yes, they mean that here. So the data that goes into the input feature that goes into the multi-head setting, so it can be quite slow, this module, so because of the number of the channel. So what they did was to introduce a pointwise convolution to reduce the damage, the number of channels before we take it into the multi-head self-attention. So I think I might be confusing you here. So I think it will be better if you see it from a visual point of view. So what I'm saying is that the input feature map, we use this pointwise convolution to reduce the number of channels before it goes into the multi-head self-attention. This is mainly because based on the experimentation, they realized that actually when we have large channel dimension, this component or this module here can actually take more time, can increase latency in a way. So that's that. Then they introduced this shrinking ratio R, which is for determining the channel reduction. Then they said that we utilize batch normalization for efficient deployment. Like I said here, that essentially they decided to use batch norm and ReLU. Then they dropped the layer norm, and they also dropped the GELU because of, based on the experimentation, they've realized that they increase latency. So they state that the next transformer block is equipped with multi-head convolutional attention module that operates with the self-attention module to capture multi-frequency signal. Yeah, this is one thing that I also said, was that so essentially we can think of like this multi-head convolution. It captures the high frequency signal. Then this multi-head self-attention, it captures the low frequency signal. So by that I mean global and local information. Then because of we combining these two components, we call this multi-frequency signal. So again, from a visual perspective, how are they doing it? So we can think here we have a multi-head, right? And we have a multi-head convolution. So you can see that we'll be taking whatever is coming from here, and we're going to concat with the output from there. So we're concatenating the output of the multi-head self-attention and the multi-head convolutional attention. Okay. Then the final step here, they have this multi-layer perceptron. Essentially, that is just to extract more essential and distinct features. So all of these operations are denoted as follows. Okay, so I'm just going to scroll down. So they state that, like I mentioned, they leveraged page norm and ReLU, so they didn't use the layer norm and GELU due to the performance reason. Anyway, let's look into the next hybrid strategy. So the motivation behind the next hybrid strategy was that the author realized that like some of the hybrid strategies, they just stack the transformer block in the last few stages, right? Therefore, the shallow stages fail to capture global information, and the ability to capture global information in the shallow stages is quite important for tasks such as segmentation and detection tasks. So therefore, they decided to come up with a strategy on how they can actually combine the layers or the components that capture local information along with the components that capture global information. So they creatively stack convolutional block and the transformer block with n+1 times L hybrid paradigm. So essentially they take the convolutional block and they have a number that they experimented with. So meaning that they times this block by a specific number, this could be 5. Then they add the transformer block at each level. So what I'm saying here is that, for instance, let's say at the first level, we can have convolutional block, for convolutional block plus maybe transformer block, maybe the next level, just like so. But that's what they do in here. So that's why this L denotes the number of levels. So, okay. Then they state that the transformer block is placed at the end of each stage, which enable the model to learn global representation in the shallow layers. So they mean that like those layers that are close to the input, right, they can also be able to learn the global information now, which I find to be quite important, because not only the entire architecture learn global information at the end, but also the kind of like the shallow layers, they can actually have the global information, and therefore each level have a global information. So I quite find that to be quite good, honestly. So they state that expanding the model size by enlarging the n pattern, simply adding more convolution block is not the best choice. It implies that the value of n in this pattern may seriously affect the model performance. Therefore, to build a model with similar latency for fair comparison, we stack L groups of this pattern with the value of n is small. So we found that the convolutional block and the transformer block in this pattern achieves better performance compared to this. So what they are saying here is that having this level, I call it level, I don't know if like, yeah, but having this level, we can achieve better performance. And this is because they are repetitively combining low frequency signal extractors and high frequency signal. So essentially what they're saying is that it's for each level, we keep on getting local and global information at the end. So doing this way, they realize that actually they achieve better performance in that way. So that's what they said. Then they state that with n equals to 4 in the state stage, achieving the best trade-off between performance and latency. So if n, the number of convolutional block, is equals to 4, they achieve better performance and latency based on their experimentation. I think that's all. Honestly, this is more like implementation, which we're gonna get into this on the code side of things. But yeah, I think quite impressed by this paper. I really enjoyed going through it. And I really like their techniques that they used. So yeah, let's get into the code and try to go through and try to understand it from there. First and foremost, credit to the authors for their great job. So there's certain functions that they reference in the repo, but when we go to those functions, I'll actually point you to where they are lying within the repo. So so within a specific code, they might be referencing some of the files from specific repos. So I'll actually show you when we get to those part. So the first thing that they did was to initialize the norm EPS. So you can think of this as we try to avoid the division by zero problem. So this can occur, especially if a feature has a zero variance. The second component that we look at into is the convolution batch norm ReLU. So this is a standard convolution whereby we have a convolution and we have a group. This group function essentially enable us to split the input channel into multiple groups, and we can apply separate convolution operations. However, if it's set to 1, it's just the standard convolution. Then what we do is that we apply the batch norm and the ReLU. Just like I said, they didn't use layer norm or GELU in this case, and this is mainly because based on the experimentation, they realized that these two um, uh, they were fast essentially. So, so from the visualization perspective, this is the first component that they are referring to. And you can see here they have this n to show that this convolution called stem can be repeated multiple times, and we will get to the point whereby this component is being replicated multiple times. So now looking into the patch embedding. So the patch embedding essentially is used to extract features from the region of the image. So we convert an image into a sequence of fixed size patches that can be processed by the subsequent components. So the first thing that I'm going to talk about is the norm layer. So essentially this partial function, essentially it's a more like a handy function that actually enable us to um, parameterize this batch norm with this argument norm EPS. So all the time we don't have to call batch norm and pass the maybe the output channel in this argument. So we just need to call this and pass the output channel. So you can think of this as more like a handy function that reduces the number of code that we have to write. Then we have this condition to check if stride is equals to 2. The intuition behind this is to actually be able to capture global information while we reduce the spatial information. So we use this, we apply this average pooling with stride of 2, and yeah, count including paired equals to false. Then we have this convolution. This is a pointwise convolution, a one-by-one convolution layer. Then we apply the norm layer. So in a case whereby the input channels do not match the output channel, instead we apply this identity function. So we can think of like the identity function, a simpler function that returns an input unchanged. Then this is going to be more like an average or average pooling. Then we apply a pointwise convolution of 1 by 1. Then we apply the norm. However, if we have if like the stride is not equals to 2 and the input channels are the same, then we apply our average pool is going to be an anti-team function including the convolution, including the norm. So yeah, that's what we do. So taking a closer look at the multi-head convolutional attention, we still pretty much have our same batch norm. Like I said that in the paper that the multi-head convolution essentially is a group convolution of 3 by 3. So for instance, let's say that our output channel was 64, then the head dimension was 8. So 64, if we do an integer division of 64 by 8, it's going to give us 8 groups. So this means that the input channel will be split into 8 groups. Each group will be convolved with 8 filters. What we do is that we apply the batch norm to our output channel, and we apply the ReLU, and we then project this using a pointwise convolution. Okay, just as a refresher, you can see that this component is this part here. So we know that we have this group convolution, we have this batch norm, we have ReLU, we have a pointwise convolution of it's point 1 by 1. So, and we do a forward pass like so. The next component is going to be the multi-layer perceptron. So we can clearly see that this follows the what's it called again? The metaform architecture, whereby we treat this multi-head convolution attention as our token mixer. Then we have this multi-layer perceptron. So as a refresher, if we take a look at the diagram, I'm just going to try to erase this to kind of like make it nicer. So we have this input, it goes into the multi-head convolution, which is coming from the patch embedding. Then we take this, we push it into the multi-layer perceptron. So we can see that we have these residual connection within each sub-layer of this next convolutional block. So this is self-explanatory. All these components that we're applying inside here. So this is what we call a channel multi-layer perceptron. So I think in that paper of the meta format, that's what they call it. Then here we're just combining all of these components that we spoke about into one block, and we call this block the next convolutional block. So for instance, we take the patch embedding, and we have the multi-head convolutional attention, and before we apply the multi-layer perceptron, we make sure that we apply the patch norm and we regularize our model. So pretty much the next block is just a combination of all these components that we just discussed above. The next component is going to be the multi-layer perceptron. Before we look into the multi-layer perceptron, within this multi-head convolution, I'd like to add that essentially the group convolution allows the model to learn multiple feature maps from the same input, right? So each group of filter will learn different feature maps, and the final output will be the combination of these feature maps. So it's the same concept of like multi-head, how it works within the attention. So this can actually help the model to extract more discriminative features from the input and improve its performance of the image processing task, right? So that's the significance or rather the intuition of this, why the author also called it the multi-head attention. So the next component is going to be the multi-layer perceptron. Before we get into this, just as a refresher, we can think of this as like I said, this is more like a metaformer architecture, right? So we applied this first component, which is called multi-head convolution. So we can think of this as a token mixer. Then we pass this into our multi-layer perceptron. So we have these residual connections. So when I take a closer look at the metaformer, they have even a norm layer here. Okay, so now we're looking in this component, the multi-layer perceptron, right here. So just to be clear, this multi-layer perceptron in the metaform paper, they refer it as a channel multi-layer perceptron. So essentially, we can think of this as like a ratio of hidden units to inputs. Then we try here to transform the input into higher dimension to increase the expressive power of the model. We can see by this higher dimension. Then we apply the ReLU activation function. Then we bring this activation function here. So here we can see that we transform the hidden feature to lower dimension with this 1x1 convolution. Then we apply the forward pass. So yeah, I think that's the most important thing. I'm just gonna go to the next component, which is the next convolutional block. So here essentially is just the stack of the components that we just discussed now. We have the patch embedding, right, which we just discussed also. So this is the module that apply the convolution operations to the input image. Then we have the multi-head convolutional attention. Also, it is a mechanism that allows the model to focus on different aspects of the image input. Then we have the dropout path, which is this is a regularization technique that randomly drops some of the neurons during training to prevent overfitting. Then we have this the batch normalization. We apply the batch normalization before the multi-layer perceptron, which is also known as a channel multi-layer perceptron. Then we have this function is batch meshed. So I think this is a flag to check if batch normalization and multi-layer perceptron have been meshed or not. But pretty much here, next convolution is just the stack of these things that we just explained above here. So yeah, I'll say that's what it does. So what we need to do is that because like I said that we have this when we first apply the patch norm, we have these residuals, so connections. So we just need to make sure that we add after applying the what's this, the multi-head convolutional, we add this to the input, and we do this after we apply the multi-layer perceptron. We add the input after it has been transformed by the multi-layer convolution. So this is also shown in this diagram right here. So we can clearly see all of that implementation in this diagram right here. So we just had a look into the next convolutional block. So we're going to take a closer look into the efficient multi-head self-attention, whereby we take in the dimension, output dimension, and the head dimension, which is by default equals to 32, and query key value bias. So what we have here is that the number of heads is going to be, we're going to take the dimension and do an integer division by the head dimension. Then we're going to have the self scale, which is going to be the query scale or the head dimension by negative 0.5. So essentially here, I think essentially this is more like a scale factor for the dot product of the query and key matrices. Then here on the self.q and self.k, self.v, these are like context encodings matrices. So the q module takes the input and is going to apply the linear transformation to it and return the matrix. Then we have the self.project. So here we're going to project the output of the attention back to the original dimension. Then we have these, we try to regularize the attention and the projection layer. Okay, so like I said, that there are certain functions that they will be using that are coming from different repositories. So in this case, I am interpreting this as like they're trying to use like batch normalization statistics from a previous layer within this current layer. Okay, so yeah, that's that. Then what we have is that we have this forward pass, whereby we take the input feature and we extract the dimension of this input feature, and then we pass this input feature into the query matrix or the encoding context. Then we try to reshape this into the batch size, number of heads, sequence length, and channel, right? And essentially to give you a better, some sort of like a better context. So this is essentially done to facilitate the multi-head self-attention mechanism, right? The purpose of these permutation is to split the channel into multiple heads, so each head can attend to different parts of the input sequence in parallel. Okay, so by doing this, each head can learn to attend to different information and provide a diverse representation of the input sequence. So this leads to a more robust expressive representation. So it can help the model to learn the relationship between the input and the output. Okay, so we do some transformation if the SR ratio is greater than 1. I think here we apply the average pooling. Then when we are done with transforming the key and value, we try to get the dot product of the query and key, and we multiply this by this scale. So this is like how the attention work. So if you're familiar with the self-attention mechanism, this might look familiar. Then we apply the softmax. So after this, we always apply the softmax. Then we apply the dropmax. We apply the dropout. Then we take the attention and we multiply by the value. So all of this is literally self-attention. This is literally self-attention. So after we've done that, we try to reshape this in the way that we got the input. By that I mean like how we got the input, we try to reshape it back toward how we got it. So we did the reshaping, the permutation for the attention purpose, but now we take it back to how it was. Then we apply the self-projection, then we apply the dropout within this self-projection, and then we return the X. So from a visual perspective, essentially this is the component that we applied here. So this component here, so we had within the multi-head self-attention, we applied the batch norm, we had the query, and we took the key and the value, we applied the average pooling within those, then we had this multi-self-attention mechanism here. Okay, so the reason why we needed to make sure that the output have the same dimension as the input is because of these residual connection, and also it's because of we needed to maintain the correct dimension because we are joining this with them with the multi-head convolutional attention. So yeah, I think that's what it is. The next component is going to be the next transformer block. I'm not going to go too much into depth into this because I feel like it's just like integrating all of these things together that we just discussed. So you're just combining them. Like so, this is this component right here. So it is just this component here. So we just need to combine these together. So that's what this next transformer block does. So yeah, so I think these are the input. However, some of these input like SR ratio, I think this refers to the ratio between the input and output spatial resolution. Then we also have the MLP ratio, which could be referring to the ratio of the number of channels used in the ratio of number of channels in the multi-layer perceptron to the number of channels in the input sequence. Input sense, I mean to say. Then we have the mixed block ratio. So I think this one is the ratio of number of channels used in the multi-head self-attention mechanism to the number of channels in the output tensor. Then we have head dimension and attention drop. So like I said, that we're just trying to combine all the components that we discussed about from I think here we're just defining them. So I think the interesting part will be this here. So as you can see that we take our input and we apply the page embedding and we project this, then we take this and apply it within the multi-head convolutional attention, and you can see this residual connection here. then we have an X, then we concatenate, as stated there, that we concatenate the multi-head self-attention path. That's why you see here concatenate, because in the paper, like you still remember, they said that we don't want to lose the low and high frequency signals. So hence here we try to get all the information. Hence you see here this touch.concat. So we take this X and we take this output and we concatenate this. But yeah, and we apply the multi-layer perceptron, which is the final, and also it has this residual connection, like so. So if we take a look at this, and we can pretty much see all the things that I'm talking about. They are also visuals here. So we apply this multi-layer perceptron with this residual connection. So yeah, I think that's all. And yeah, and this component here, this is the last phase which you can go about it. It's just the next hybrid strategy that I spoke about, that how they try to each level, how they try to replicate the next convolutional block, and how they add the next transformer block. So we have like I think they said they have four levels, I forgot, but yeah, somewhere there. Then you can see how the first convolutional layer is replicated how many times. So I feel like this stage is just like bring everything together, and yeah, that's what it is. But yeah, I think the most important thing was kind of like give you a high level overview of like the code and how everything comes together, and some of the method that I find quite interesting. Hopefully I'll improve how I explain as time goes by, and I'll try to make sure that yeah, but if you like the information, leave a like, and yeah, I'll see you guys in the next one. Bye.